Yes, sir.
Okay, good. Okay. Okay, start the recording. Started. So let me share the screen. So yeah, is this slide visible? Hello.
Yes, sir.
Yeah, yeah. So any questions? In the last class, we are discussing about threads, right? Different thread implementation models we discussed, like many to one, and one to one, many to many. So there are different thread models we discussed, multi-threaded models, and we also seen the thread libraries in context of the P threads, like so how the threads are created and how the it is coordinated with a simple example we discussed, right? And yesterday we started discussion on the implicit threading. So in that, one of the ways where the we can implement this implicit threading using thread pools, right? So these things we discussed, and also basically these thread pools are used in the context of, for example, in the case of client server model, where we have a server and a lot of clients used to take the service from the server by connecting to the server, and then by sharing the request. Then the server used to respond by giving appropriate the information, and so this can be done effectively. You can done using threads, multi-threaded server, where whenever the client request arrives, then a thread can be created, and the request will be passed on to thread. So, but that will be, it takes time. It is effective compared to the creating a process and all, but still it takes some time, because for every request, a thread has to be created, and then this request has to be passed on to that. So it is some amount of time it will take, and then since there are lots of requests used to be there, so therefore the thread creation itself is a bit of overhead and it takes time. That means the overall efficiency of the system will not be much efficient, because for every request you need to create a thread, and that even though thread creation is uh, simpler, and simpler means the time it requires to create a thread compared to change is very less, but still, as you had to create more number of threads, so it's time consuming and all. So instead, the concept of thread pools is nothing but at the beginning, that means when you start the system or when you just power on the server, at that time itself you can create a thread pool, and where this thread pool is nothing but you create a threads as some finite number of threads, and then they are waiting for the job to perform. So whenever the request arrives from a client and all, then the request should be directly passed on to a thread, because there are lots of threads that are available in the thread pool and all. So that way the thread pools can be used for serving the request for the clients, like without like, because they created at a time, and then they need not like that creation time can be minimized. And the second advantage of thread pools is that the thread pools will provide a limit on the number of threads that can be created by a server and all. Because otherwise, whenever the request arises, if we keep on creating a thread, then at a certain during the peak time, where the number of requests will increases, and at that time, if you keep on creating a thread for every request and all, then the resources will be exhausted. So to limit that, in case of thread pools, where you can fix the size of the thread pool or the number of threads that are created, and with that you can able to manage the resources also very effectively. And the another thing is that the most sophisticated point in these thread pools is that the thread pools can be dynamic. Like it means that based on the traffic or based on the request, the thread pool size can be varied dynamically. It means that if there is very less traffic at that time, the pool size can be kept smaller. And then if there is a maximum traffic or very peak traffic at that time, you can keep the pool size to be the maximum, whatever it's possible. So that way the thread pool size can be dynamically varied. So with that, the resources can be effectively utilized and all. Otherwise, no, like if you can design the thread pool for a peak traffic, and it's just necessarily wasting the resources by creating several threads without offering a job, or without giving tasks to all the threads and all. So the next one in this implicit threading is the it's open MP. It's here the MP refers to the multiprocessing, and here the idea here is that in this open MP, like where it is supported by the compiler and the like libraries and all, where here the user, when he writes the code or when he develops the application program, so he can just insert the compiler directives wherever the threads can be generated, where the threads can be used for effective computation and all, or for parallel computation. So the regions where the threads can be incorporated, so those will be indicated by the compiler directives, where the compiler will see them and then it creates the threads and it perform the it can able to run the that activity of that particular segment parallelly by exploiting the multiple cores and all. So that way you can see here in this, you can hear a for loop where you are just adding the two arrays, just performing the sum of two arrays element by element and all. And here in this case here, the like you can the user can specify that, yeah, here at this loop, at the beginning of the loop, there is the threading can be carried out. So the compiler will insert the threads, or will create the threads over here and all, that depending upon the number of cores it contains, and then this particular portion will be run parallelly so that it can be effectively carried out. Yeah, similar to that will be like a grand central dispatch. This is also very similar to the OpenMP. And here this is implemented by the Mac OS X and iOS operating systems. So here the user will specify the entire program is divided into blocks, right? And the blocks are specified by the curly braces with the beginning of a curly braces, where the caret symbol will be inserted. So it indicates that, yeah, this is a block where this block can be parallelized. That means you can effectively utilize this block and run by multiple cores and all. And here in this Grand Central dispatch, from the name, here the process can be viewed as a blocks, where there are some blocks will be of a serial nature and some blocks will be of a parallel nature and all. So then after dividing the program into blocks, and then these blocks will be placed in a queue, and this dispatch queue will release the blocks one by one, and then whatever the available threads are there from the thread pool, and it will be given access to the thread pool. So with that, the block will be executed. And here, basically, as I mentioned, that the blocks of based on the nature, there are two types. One is the serial blocks, and other one is going to be concurrent blocks. It means that the serial blocks means the block has to be executed, all the statements to be executed in a sequence. Whereas the concurrent blocks means actually here there you can able to run the parallel activity over here. So therefore, each of these blocks, like the serial blocks and concurrent blocks, they will be maintained in separate queues, right? And here, in case of serial blocks, where a block will be, these blocks will be maintained by some order, like a first come first served or FIFO order, first in first out order, where the block will be dispatched from the this particular queue, and it will be given to the thread. It will be given to thread. And once that block is completed, then the next block will be taken out from FIFO and it will be given to a thread and all. So that way, in case of serial blocks, where the threads will be, that means the blocks will be executed in a sequence, like one at a time will be taken out from the queue and then given to the thread and it will be executed. Whereas the concurrent queues, it means that here the blocks can be executed in a parallel way. It means here instead of one block at a time, here you can take a multiple blocks, and then these blocks will be given to the the threads where they can be able to run parallelly. And here again, these concurrent blocks where they have a priorities over here and all, where that depending upon the task you are executing and all. So based on that, we have three broader priorities like low, medium, and high priorities and all. And with that, the threads will be assigned to these concurrent blocks, and then they will be executed. Yeah, more or less actually here in all these cases, the underlying point here is that so the application programmer, he will suggest that, yeah, these are the blocks, these are the places where the threads can be exploited, where you can create a threads and you can exploit the multi-threading over here and all. So that way here either Grand Central Switch or like OpenMP or the other one, the thread pools anyway. So these things will take care of that, and they'll try to exploit that, and without the human intervention at each point, at every point in the application program and all. Yeah, then there are some when you are performing a multi-threaded process to be executed, well, execution of multi-threaded process, you come across certain issues that need to be resolved, that need to be you had to think of or you had to resolve in case of process how they used to be implemented, and if the process is converted to a multi-threaded process, then how these issues will be can be carried out, or how these issues will be addressed and all. So these are the certain issues, some of the issues that we are going to discuss over here, like in case of fork system call, we know that the function of the objective of fork system call and all, it used to create a process, and then afterwards the process may be the same as the parent process, or otherwise sometimes the process can be replaced with a new process using exit system call. So here in case of multi-threaded process, so how these fork and exit system calls can be used, what are their semantics and all. So we'll see that what are the issues over here. Similarly, signal handling means it means that when the process is executing, that means the sequence of instructions are executing, some signal may be arrived. That means if some event occurs, like that may be erroneous event, that means when the program is executing and when it enters into some like erroneous result or some error is going to happen or something, then it will be informed that, yeah, the signal, it will be informed through an event. That means whenever an event occurs with the execution of a program, right, during the execution of program, it's known to be a signal. And again, these signal will be like of type either synchronous or asynchronous. It's a kind of like interrupts kind of a thing. Either it will be synchronous or asynchronous. So synchronous means the signals are arised or the events are occurred due to the execution of the program, the present program. And asynchronous means they are not related to the execution of program, and from outside the signal is arrived, right? And then you need to take appropriate action and all. Right, we'll see that for the synchronous and asynchronous signals, like how they are different, like in case of a process how these are handled, and in case of a multi-threaded process, the multi-threaded process means a process have multiple executions possible. So in that context, how these signals will be handled, which thread will handle, or is it that all the threads need to be handled, or like if there are some group of threads, or like a specific thread, or the current thread, whichever causes this particular signal. So all these things we'll try to see that how they are, how they were handled in case of the multi-threaded process and all. And similarly, the cancellation, thread cancellation also. Suppose we want to cancel a particular thread, a target thread, then how do you cancel that? And again, there are different modes of cancellations: asynchronous cancellation and deferred cancellation. We'll see that what are these two. Like with the thread local storage. So far we discussed, we mentioned that the threads will share the data from a process. It's fine. But there are some cases where when the threads are in execution, they maintain some local data, or they maintain some data which is local to a specific thread, local to a particular thread and all, right? And there are some data where it will be shared across the threads and all, where the data is with respect to a process and all the threads can able to share the data. But there are some cases where threads maintain the local data. It means that that data will be appears or will be available for that particular thread only. So we'll see that what is meant by that thread local storage and where it is required and all. And finally, the scheduler activations. So scheduler activations means basically this point or this particular issue is uh, is related to the interaction between the kernel threads and the user threads. We have seen that, like in case of like many to many models, where there are certain number of threads in the user space, and then there are certain number of threads in the kernel space. And these user space, the threads, whatever is present in the user space, they are mapped to the kernel level threads and all. So then in that case, well, some activity, some of the user thread is mapped to kernel thread and where it is executing some system call. And in the process of execution of the system call, there may be some event may occur. It may be blocked or it may something may happen at that time. So this information has to be conveyed to the user level threads or the scheduler, which schedules the user level threads and all. So in that case, how these kernel level threads will inform that. So there will be specific mechanism known to be upcall handler and all. So with that, the kernel will inform to the thread library that is present in the user space and about the a particular thread, a particular user thread and all. Yeah, this particular user thread has tried to access the IO, and as a result of that, that IO is not available. So therefore, the particular thread need to be blocked. So that information will be passed from the kernel because that information is available at a kernel, and that the way the kernel will share that information to the user level thread or user level thread library using an upcall, and we'll see that how that happens. And yeah, coming to the semantics of fork and exit system calls in the context of multi-threaded process. The issue here is that actually whether when you are performing the fork system call in a multi-threaded process means there are several threads are in execution. Suppose a particular thread, when it's execution, and it encounters the fork system call, when it encounters the fork system call. So there at that time, here the for as per the fork semantics, so it will create a child process. It will create a child process. So here, but here in the process, there are several threads for there, and one of the thread has executed the fork system call. Then in that case, actually here, how the fork system call will be executed. It means that whether the fork system call will duplicate a child, right, will create a child, and where that particular child has like all the threads, whatever the parent has, like all the threads are required for the particular child, or only the thread, whatever is created, only that particular thread is sufficient. So in doing that, while for this, in these, there are two possibilities. One thing is that as per the fork system call, you are creating a child and the child has exact replica of a parent process. So it means that there are four threads are there, assuming that one of the thread has executed uh, has executed the fork system call. So in that case, there are two possibilities. One thing is that with this fork system call, you are creating a process, and that process has, again, all four threads should be there, an exact replica of a parent process. That is one thing possibility. And second one is that the fork system call, it will executed by a particular thread. So whatever the thread that has been executed is that created process contains only that particular thread. So these are the two issues over here. And here the Unix systems, actually they have the two versions of the fork. They implement the fork in the two versions, and one of those two versions, whatever I have mentioned. One thing is that by one implementation will create a child with the exact duplicate of a parent process. It means that whatever the parent process, all the threads, whatever is there, so the exact replica or the child is just duplicate of a parent process in a normal fork system call. And the other one is that the fork system call will try to create a child process which contains a thread, whatever the fork system call has been executed. So in these two versions, so which one has to be used, right? So is the child is the a complete replica of a parent process, entire parent process, or is the child contains a particular thread, whatever is executed and all. So that depends upon the exit system call. Suppose, for example, if a fork system call is followed by the exit system call, it means that whenever you are using exit system call, it means that you are creating a new process. That means fork system call itself create a process, and that process will be initially it will be a child process, right? And in that child process, we have if you want the child process has to be replaced by the some new process and new program, then by using exit system call, whatever the process that need to be loaded, so we'll load that using exit system call. That we have seen in when you are discussing about process creation and all. Otherwise, suppose if the process need to be like exact replica of a parent process, if it is required, then in that case, the exit system call is not required. Just by using fork system call, you create the exact replica and afterwards you can continue that. So here, in the case of multi-threaded process, we have that two variations of fork will be there. So here, if you see that if there is exit system call followed by fork, so in that case, we need not create a child, the exact duplicate of the parent process and all, because we know that if the exit system call is following, it means that whatever the process that is created will be a new process because that is created afterwards. The exit system call will replace that with the desired program. So in that case, there is no need to create all the threads of the parent process and all. It's again like it's involving and a lot of memory space is required, other resources are required and all. So instead, actually here, if the exit system call is following the fork system call, so at that time, the fork will take the second option. It means that the fork will just create a thread, whatever is involved in creating, in implementing this fork and all. Because if there are four threads are there, and one of the thread is executing fork system call, and then if it following the exit system call, then the fork system call will create a process which contains only one thread, whatever the thread that is responsible for creating that one. Whereas if there is no exit system call, if there is no exit system call following this, then the fork will create the exact replica of the parent process and all. It means that if a parent process has four threads, then it just share the entire the address space of a parent process and all. So that way here, the fork system call can be used in these two versions. That depends upon whichever the version that depending upon the exit system call. If the exit system call follows the fork system call, then in that case, the fork system call will create a process with only a particular thread, only a specific thread. Whereas if the fork system call is not following the exit system call, then it just the fork system call will create the process which contains all the threads of the parent process. So that way, the execution of fork, implementation of fork will be slightly different from the normal process and all. Then coming to the signal handling. So as we are already aware of that, because we heard about, we discussed this even in the architecture also when you're discussing. The signals, in particularly in the context of Unix system, it's nothing but it just notifies the process some event has been occurred. It notifies the process that an event has been occurred. And as I mentioned that that event may be asynchronous or asynchronous. Synchronous means the event has occurred due to the execution of the current thread or current process and all. That is a synchronous signal. Asynchronous signal means it's nothing to do with the program execution. And the signal has been or the event has been arrived or event has been occurred due to the external event. That may be power failure or somebody just want to kill the process, for example, using Control C, right? Or some other thing, whatever. So that way the signals may be either synchronous or asynchronous. And in case of multi-threaded process, how do you handle these signals? If it's a process having a single threaded one, then whatever the signal arrives, that signal will be delivered to a process, right? It is up to the process. If the process has a particular signal handler, a specific signal handler, then that signal handler will be implemented, that will be executed, and the appropriate action can be taken. And suppose the signal handler, specific signal handler is not there, it's not defined for a process and all, then in that case, the operating system will take over. That means operating system will make use of a default signal handler, and then it will run, and then the appropriate action will be taken and all. So here the signal handler is used to process the signals, as I mentioned, and the signal handler, the signal is generated by a particular event, correct? And then the signal will be delivered to a process in a normal sense. And if the process has a specific signal handler, then that particular signal handler will be run, and then appropriate the message will be delivered, or like if the process to be terminated, it will be terminated, or otherwise a process will be simply continued by just skipping that particular instruction, or the process may give you the output saying that the error has been occurred or something. So likewise, the signal will be handled by specific signal handler defined by a process and all. Otherwise, if it is not there, then the operating system will handle that. Just by ignoring that, sometimes some of the operating systems will ignore the signals and it will continue, and some of them will take appropriate action and all. Like they will run the corresponding service routine, and with that, either the process will be terminated, or skipping, or just moving the control to some other place, that can be done. So as I mentioned here, the signal handlers are of two types. One is the default handler, and other one is a user defined. Default handler means actually here, whenever the signal arrives, by default, the operating system has to handle that. Operating system will handle that the signal and all, whether it may be synchronous or asynchronous. User defined means a process, an application user, an application process, the user, application programmer itself will define the signals, and he will incorporate in the part of a process and all. So whenever a particular signal arrives, and that particular signal handler, if it is available to the process, then that particular signal handler will be run, and then appropriate message will be communicated and all. Yeah, each signal has a default handler, as I mentioned, by kernel, run by the kernel when to handle the signal. Otherwise, user-defined signal handler, it will override. That means if a particular signal, it has already signal handler defined by the user or defined by the application programmer, then it will override the default handler. If it is not there, then the default handler will be run by kernel. And if the particular signal handler is available in view of the process and all, then that particular signal handler will be override. That means instead of default handler, this particular user-defined signal handler will be run. Right? Whenever the signal arrives, then we will check that whether the signal handler, user-defined signal handler is available, then it will be run, it will be executed. Otherwise, if it is not there, then the operating system will take over. Yeah, as I mentioned, if it is a single-threaded process and all, then the signal will be directly delivered to the process. Signal will be directly delivered to a process, and it is up to the process. If there is a signal handler is available to the process, then it will be run. And if it is not available, then kernel will take over. And now here the issue is that suppose if the signal is arrived or the signal is generated, then where the signal has to be delivered, because it's a multi-threaded process, there will be multiple threads are in execution, assume that. In that case, where this signal has to be delivered, which thread will receive that signal? So there are different ways here and on. Suppose, for example, if the signal is generated due to the synchronous, that means if it is a synchronous signal, it means that this signal is generated because of a specific thread of execution, because of a specific thread of, because of some instruction is in execution by a particular thread. In that case, the synchronous signals will be delivered to a particular thread, whichever the thread is the cause for generating the signal, so that then the particular signal will be delivered to the specific thread, right? And so that way the thread will manage that. If it has a signal handler, then it will manage. Otherwise, the OS will do that. Suppose, for example, the signal is asynchronous signal. It's nothing to do with the execution of the threads, like it is from external signal, right? So in that case, how do you handle that? So there are different ways where the different operating systems will handle them in a different way. And here in the process, the different various threads are there, and the multiple threads. There are, for every thread will be defined that every thread will be defined like they block certain signals and they will allow certain signals. It means that when a signal is arrived, some threads will allow the signal, will receive the signal, and some threads they will not listen to that, they will block the signals and all. So that depending upon that, some threads, no, they meant for accepting or receiving certain signals, and some of them will block, and some threads will block all the signals, and some threads, no, they will block, they will receive all the signals. So likewise, there are different ways. The threads will be they can either they accept the signal or they can simply block the signals and all. And in that case, suppose the signal is arrived, assuming that this is an asynchronous signal, at that time, this signal will be passed on to a thread, right? There are multiple threads are there, right? So again, which thread to be given? So therefore, first the signal, whenever it's arrived, it will be given, it will just expose to a particular thread. If the thread is not blocking that signal, then the signal is directly delivered to the thread and the thread will manage that. Suppose if the thread, whatever you are exposed first, that thread will block this particular signal, then you have to opt for, then this particular signal has to be delivered to or will be given to, will be checked with the another thread. So likewise, yeah, hello? Yeah, yeah, is that, am I audible? Hello?
Yes, sir, we are audible.
Yeah, right. Yeah, if you have any issues, then please remind me, please tell me. So that way there are issues with the signals and all. So here there are different possibilities here. It was mentioned here over here. And that depending upon the nature of a thread, actually, if the signal when arrives, when it given to a particular, when it is given to, want to give it to a particular thread, if the thread is blocking that particular signal, then we'll try for some other thread. So likewise, if the first thread accepts that signal, then we'll stop. Then we deliver the signal to the thread, and it's up to the thread to manage whether it can able to handle on its own or it can able to. It takes the help of a system call or operating system to handle that signal, right? So that way, in case of multi-threaded process, there are different possibilities are there. So with that, actually, the signals will be handled. Hmm. Then coming to the thread cancellation, as I mentioned, like first of all, why the threads need to be cancelled? As we have seen that process cancellation also required when the parent process create a child process, then sometimes no, the parent forced to cancel their children with the different reasons, right? We have discussed that. Similarly, here also in case of threads also, sometimes the threads need to be cancelled. And one of the examples will be, for example, we have a huge database, for example, and in that actually you want to retrieve some data. You have some query or some request and all, and then we need to find out the response to the query. So for that purpose, and since the database is very huge, we don't know where the response or where the result is available. So in that case, what we can do is that we can create a multiple threads, and then we'll pass this multiple threads to search the database in the partition wise. That means suppose we have a database, and then the entire database will split into some number of blocks and all. And where for every block we'll create a thread, and then the thread will be given for searching the database for a given query and all. And so that way you can use the multiple threads for searching purpose. Like the same way, for example, when you are searching for a web page or when you want to get a desired web page and all, at that time when you send the request will be sent to the multiple servers in this vicinity. And then if one of the servers send the response, and whatever the nearest or whatever is available server and all, then afterwards the threads whatever the simultaneously generated, and they need not be required and all, because already the response whatever is required that has been received, right? So the same way here also, when the multiple threads are generated to search the database, and after once you receive the response from one of the thread, then the remaining threads need not be processed at all. The remaining threads which are in the search process and all, they should be cancelled, because already whatever the response that is required, that is available from that you received from one of the threads and all, then the other threads, whatever the remaining threads, n-1 threads, whatever is created, which have been assigned the task of searching, so that need to be cancelled and all. So likewise, there are occasions where you need to cancel the threads and all. And here, how do we cancel the threads? Actually, there are two different modes of cancellation. One is known to be asynchronous cancellation, other is known to be default cancellation. The asynchronous cancellation means you need to terminate, or the desired thread that need to be cancelled will be immediately cancelled, will be immediately to be terminated and or cancelled. And deferred cancellation means actually it will allow the target thread to periodically check, or it will allow the target thread to terminate at a safe point, or will be cancelled at a safe point. Because as I mentioned, this thread, suppose for example, the threads are in the we have multi-threaded process where the thread is involved in the data manipulation of some shared data, for example. And when the when this particular thread is in the in the process of manipulation of data, and suppose this thread has to be cancelled, and suppose if it needs to cancel, if you just immediately cancel this particular thread, and then it's the process of data manipulation, data modification or whatever, and if it is in the middle, and if you cancel that immediately, then there is a problem of data inconsistency may be there. So therefore, when you're in case of deferred cancellation, when you're canceling the thread, you just inform the thread that yeah, the thread cancellation is enabled and all. And after that, the particular thread that will check the status of this cancellation from time to time at periodical intervals. And then whenever it's enabled, whenever it sees the enabled, then it will not cancel immediately, it will not terminate immediately, but it will see that whatever the next safe point, the nearest safe point, and it will execute till that point, and at that point it will simply the leave. It will simply the terminated and all. So those are known to be the thread safe points and all. At safer points, it will be terminated. And this is known to be the deferred mode of cancellation. Whereas in case of asynchronous mode of cancellation, it will be threads will be immediately need to be terminated. And so these are the thread the support for this cancellation. We have this is thread creation, and this one is the pthread cancel the specified TID. It used to cancel that used for cancellation of a thread. And yeah, as I mentioned that here, like a thread, there are different status disabled and enabled. Disabled means actually you are not requesting for cancellation. Enabled means they are requesting for cancellation. And again, there are modes, deferred mode and asynchronous mode, right? And here, as I mentioned that like a thread, when it's execution, if it is in the deferred mode of cancellation, then it used to check the thread, the thread periodically it used to check what is the status of the cancellation and all. So it will use to check by using this one pthread test cancel and all. By using this function, it used to check whether there is a request for cancellation or not. And if there is a request for cancellation, then it just enable, or it will invoke the cleanup handler and all. So with that, whatever the resources that are attached and all, so they will be simply detached from that particular thread, and at a safe point, the thread will be cancelled and all. So that way, the thread cancellation, there are two modes. One is the deferred mode, other one is the asynchronous mode. And the problem is asynchronous mode had a problem. If the thread is involved with the shared data manipulations and all, at that time, if you terminate the thread, if you cancel the thread in asynchronous way, like immediately, then you have a problems. In case of Linux systems and all, this thread cancellation will be handled through signals and all. Like for example, whenever you are executing this particular function, this will send a kind of a signal and all, and then the appropriate signal handler will take care of that, whether based on the type of the cancellation, which is a deferred mode or a synchronous mode. Yeah. Then coming to the thread local storage. So this one, the thread local storage means, we know that like most of the times the threads will share the data which is offered by the process and all. And when it's execution, depending on application, sometimes a thread requires some local data that need to be utilized in the process of thread execution and all. Like for example, when you are for example, a thread will be like you are creating a thread to perform certain transactions, for example. Like whenever there is a request and for example, a client server model, whenever there is a request and that request will be handled by creating a thread. And likewise, so whenever there is a request, and then immediately thread will be created and the thread execution will take place. And here in this case, the thread, whatever is the thread execution for a specific request and all, and whatever the data that will be used, maybe next time also you may get a request, and that request is also of similar nature and all. And here in this case, actually here each thread has to maintain its replica of the data throughout its execution and all. Like that kind of a data is known to be thread local data, because otherwise suppose they share the data like whatever is offered by a process and all, and then there will be like that data will be treated as a global data, and then if that global variables, if they are used by threads and all, then the next time when the same data is used by some other thread, then there will be inconsistency, so that leads to a problem and all. So therefore, each thread, that depending on the application, it requires to maintain some data, and where that data will be local to a particular thread. It means that that particular thread may have some several functions, and that data, whatever is maintained locally, so that data will be visible to all the functions. And this is kind of, for example, here the local variables means it's not the local variables within the thread. Like here, the local variables means actually here they are like we know that the local variable, the scope of a local variable will be only within a specific function, within a single function and all. Whereas here the thread local data means here, so the scope of this particular local data, whatever is there, whatever the data items are there, so that will be spanned to the entire thread. That means the thread may have 4 functions will be there. Across all 4 functions, the data can be used. The data will be used, right? But the scope of local variables means the scope will be limited to a particular function, only a single function. When you come out of that function, and then those variables and those data items are not at all valid. They are not at all seen by the other function at all. So that way, this thread local data can be viewed as something similar to the static data, where you can able to, the data will be available, the data will be known or can be seen across all the functions within a thread and all. And this thread local data or whatever storage, it will be unique to a specific thread, each thread, like whatever the number of threads are there for every thread, it can maintain the local data. And till that execution of the entire thread, that local data will be there, and all the functions can make use of that local data. So that is the requirement of a thread local storage, where each thread maintains some the local data, and within that local data, and that what are the data items are there, that will be static within that particular thread and all, and they are not visible to the other threads. Yeah, then coming to the scheduler activities. So here the scheduler activation means this is basically applicable, as I mentioned, that in case of many-to-many models where the number of threads in the user space is usually more than the number of threads that are supporting those user level threads will be limited. Like for example, the user program may create 10 threads, and whereas the kernel can able to support those 10 threads maybe with the 2 or 3 threads, or maybe like whatever, very few threads, fewer threads and all. In that case, there should be a coordination between the user level threads and the kernel level threads, because the kernel level threads will actually schedule the real CPUs, whereas the user level threads and all, they will schedule the user threads on the virtual CPUs, whichever is provided by the kernel thread and all, whichever is provided by kernel thread, right? So in that case, for example, a thread is execution, the user level thread is executed on a particular CPU, and it requires IO, for example. So then this IO by system call, it's nothing but it kernel thread will look after that. And when a kernel thread is taking care of that particular system call, and suppose the system call is happen to be a blocking system call, that means it needs the input from a keyboard, but the data is not available in the buffer and all, then the system call has to be blocked. So if the system call is blocked and that is not aware of at a user level library or at user space, this information is not available. So here the kernel thread that is aware of that this particular thread is a blocking is now it's now waiting for the input. So therefore it's in a blocking state. So that this blocking the state of this particular thread will be informed to the user library, because the user level thread, there are 10 threads are there, but at the operating system level there are only 3 or 4 threads are there, and those 10 threads will be scheduled to these 3 or 4 threads. And now one of the user level thread is blocked, and that is not known to the user level. At a user library, it's not that information is not available, and that information will be passed to that user library through the kernel and all. And because the kernel thread is aware of that, because a particular system call is blocked, and that information will be passed on to the user thread library through the up call, because the kernel will give a call to the thread library which is supported at user space and all, because that library will schedule the user threads and all. So this information will be passed on to the thread library that is there in the user space, and now the user library will reschedule the threads. That means because by knowing that the current thread, one of the threads is blocked, so therefore that thread status information will be maintained there. And again, the whatever earlier that particular thread is using, that particular virtual processor and all, and that processor will be given to some other thread and all. So all these things will be handled at a user space, right? And the desired information, whatever is required at a system level or at a kernel level, so that will be passed on to the user level or user library using this upcall mechanism and all, using the upcall mechanism. So that way here, the limited or finite number of kernel threads will maintain the more number of user level threads by passing the information to the using upcall handler to the user thread library, and the user thread library will receive this information and it will update. Update means basically whatever the user thread is blocked, and that particular information will be placed in in this kernel control block, sorry, this thread control block, and then and among the other threads, whatever thread is desirable, that particular thread will be given access to the virtual processor, whatever is earlier running and all. So that way, by using upcalls, the kernel level threads will inform to the user level thread library or the scheduler, and the scheduler will take that input and it will activate the other threads among the available virtual processors and all. So that way, in case of many-to-many models and all, where the kernel threads and the user thread libraries and all, they will coordinate, and with that, the multiple thread process can be executed on the system and all. Then coming to the examples that are supporting the threads like Windows and Linux threads and all, we don't go into the details. Here just we'll mention that like in case of Windows, basically we know that in Windows, the thread model that supports by the Windows will be one-to-one mapping model. It means that whatever the user level thread, user level application creates a threads and all, for supporting that, that many number of kernel threads are created and all, right? And that will be overhead sometimes, right? If the user process creates several threads, and for supporting that, the kernel also has to maintain the equal number of threads at a kernel level, and maintaining that will be like a lot of overhead or control information need to be maintained, and that will be hectic and all. And here, in case of Windows system, where each of these thread will be maintained by three different data structures, and basically the thread contains the thread ID and a register set, which indicates the status of a processor for execution of that particular thread. And and as I mentioned, that since the Windows supports one-to-one, so for every thread there will be some control information that is there at the user level, maintained by the user thread library, and there is some other information maintained by the kernel thread also. So there will be like both user and kernel stacks will be there, and you can see here the register set, stacks, and private storage data, private storage area. All these things can be viewed as a context of a thread. Right, we have seen that what is meant by context of a process. Similar to that, we have a context of a thread, which corresponds to basically the environment, right? At the time of execution, so whatever they are involved, so that indicates the context of a particular thread and all. Like basically, there's a register set, stack, and the thread local data, whatever is there, thread local storage. It's nothing but private storage. And here the Windows basically maintain the threads using these three data structures. One is the E thread and the K thread. You can see the details here and all, executive thread block and kernel thread block. And this is the thread environment block. So this is maintained in the user space. user space, because in the Windows we have a user thread and the corresponding kernel thread will be there. And at a kernel thread here, these are the two data structures will be maintained in the kernel space, and this is the data structure that is maintained at the user space and all. And you can, this particular diagram will illustrate that how these three data structures are linked on. And you can see these two data structures are there in the kernel space, and this is the user space. And the details over here, you can, this particular data structure maintains the like the starting address of this particular thread and pointer to parent process and so on, and link to the kernel thread. So you can see it's like they are like self-defined, and all you can see that where this particular thread contain the kernel stack and scheduling information and so on. So this way, like in case of Windows, where it basically supports the one-to-one mapping and all, and these three data structures that are used to maintain the thread-related information and all. And in case of Linux threads, as we aware that in case of Linux, basically in the Linux system where it will not basically discriminate the process and threads. The Linux system will not discriminate the process and threads, and it will be viewed both of them in the form of tasks. They call it as here the terminology in the case of Linux or Unix platform, where the process will be viewed as a task and all. And here this task may be, it may be a process or it may be a thread also, process and thread. And for both of them, for creating a thread or for creating a process and all, it makes use of the same system call. The actual system call that is used to create a process is a clone. But we have seen that a fork system call, right? So that fork system call will internally we use this particular system called clone. So using the clone system call in the Unix system, it creates either a thread or it can create a process. For both of them, it uses the same system call. But how they differ, actually how the process is created and how the thread is created, that differing based on the flags. That means here when you are using a clone system call, and we need to pass certain flags information. And suppose if you set all these flags, so then it indicates that actually you are creating a thread. That means you are setting this flag means the clone fs. That means the file system, whatever is there in the process, so it will be shared. And then the memory space, whatever is there in the process, it will be shared. And then whatever the signal handlers are there of a process, and it will be shared. Likewise, whatever the open files are there, those will be shared. So if you can able to provide that, if you use the clone system call by setting all these flags, it means that whatever the process that is created, it basically sharing the same address space and same files and same signal handlers and all. So it's nothing but it's it's just it maintains a data structure which contains the pointers, and those pointers are point to the same thing, the process, parent process and all. It means it's nothing but it's a thread. We are creating a thread and all, and where the thread sharing the most of the information that is there in the parent itself, from the parent address space itself directly. Whereas suppose you want to create a child, for example. So creating a child means the child may be using the file system and other things, but it will be used in a different address space, right? So in case of a child creation, whatever these flags we have mentioned and all, so these flags will not be set. These flags will be set to 0. It means that there is no sharing at all. There is no sharing of address space, right? There is no sharing of file. That means it will be shared. Shared means it will take a copy of that and it will place in the separate address space and all. So that way, in case of Linux, the threads are differing from the process and all. In case of process creation, these flags will be reset, or these flags will be set to 0, right? In case of threads, no, these flags will be enabled. When you enable these flags, it indicates that whatever you are creating, so that created one will share the like the file system, address space, signal handlers, and so many things, right? So it means that it's not a separate entity. It just maintains the pointers and the point to the address space, whatever is given by the process and all. So that way, here in case of Linux threads and all, the creation of threads in the case of Linux is nothing but using the clone system call, the same system call that will be used for creation of threads or creation of process and all. But the difference is that the way you are enabling which of the flags are enabled, which of the flags are disabled. So based on that, the amount of sharing will be different. In case of threads, no, like all these resources will be completely shared. In case of process, where they will be like they may be partially shared or they may not be shared at all. So that varies from like process to the thread and all. Like some process they may share certain things, and they may not share some other things. So that we have seen in case of child and parent, the resources will be either they can be completely shared or they can be like partially shared, and they don't share at all, right? So that way you can see that how the thread creation is different in the case of Linux system compared to the process and all. And both of them are like appears to be similar. So therefore, there is no specific data structures for maintaining this one, because it will not discriminate whether it's a process or a thread. The only difference is that how much sharing is happening between the when you're using a clone system call and all, right? So I think this will be the last part of the threads, right? And right. So yeah, then yeah, next we move on to the next topic. It's a process scheduling. So anyway, before going to that, actually, let us take a break for 5 minutes, and then we can come back and we'll start this. So if you have any questions on the threads so far. Yeah. Okay, then. Yeah, then let's take a break for 5 minutes. Okay, then afterwards we'll come back and then we'll start the process scheduling. Right. Let me stop the presentation.